So I need to just finish up talking about polar coordinates. So first of all, I want to explain how to find areas in polar coordinates. So whereas when you had a Cartesian graph, y equals f of x, we would find the area under the curve between two values of x equals a and x equals b. Now we've got some polar graph, so r is a function of the angle theta. And so now the right thing to do is to find the area of the sector inside that polar graph between two values theta 1 and theta 2 of the angle. Let's just draw a quick sketch so you see what I'm talking about. So we've got some polar graph, so some sort of shape defined by a polar equation. And you have in mind two different angles, maybe theta 1 and then another angle, maybe that would be theta 2. And what we're trying to do is calculate that area of that region inside the graph between the radius at angle theta 1 and the radius at angle theta 2. So we want to calculate the area of the sector under the polar graph from theta is theta 1 to theta is theta 2. Okay, so the usual game to do this is you think about theta changing. So you start at some angle theta, and you think about what happens when you go just a little bit more. So you had some little change in theta, delta theta. And so this little tiny thin delta theta sector, this has area, well, this, at least when delta theta is very small, is quite reasonable to approximate that sector as though it were a sector of a circle. And then you can use the formula for the area of a sector of a circle that I think we wrote down last time, which is, what was that? That was a half a squared times the angle. And the radius here, a, that's f of theta. So it's a half f of theta squared, and then the angle for that sector is that little change delta theta. So kind of what we've got to add up to calculate the area of that entire sector, we've got to sum up as theta goes from theta 1 to theta 2, the areas of all those little tiny sectors. So that's kind of the informal idea. And then, as usual, to take the limit as delta theta goes to 0, we replace the summation by an integral sign, and we integrate from theta 1 to theta 2. There it is, a half f of theta squared d theta. So that's the desired formula for the area of that sector. So I'm just going to do one example of this. And the example I'm going to do is the curve that we sketched last time. So that was the polar graph of the circle. It was a slightly interesting circle. The equation was r equals cos theta. And if you remember from last time, that was the circle centered at half of radius a half. So now this is somehow not very interesting, because, of course, we already know the area of a circle. It's pi r squared, and the radius is a half, so we already know the answer. It's pi times the radius squared, which is what, pi over 4. But I'm doing this kind of as a reality check, so that you can see that this strange formula that we've derived does indeed do the job and give you a different way of calculating the area of that circle. This would not be the right way to do it. Indeed, we've already assumed that you know the area of a circle back when we derived that formula for area of a sector. We already assumed that. So we're not reproving the formula. We're just giving ourselves a little reality check that our formula for area of a sector is doing the right job. Okay, so we're going to use the formula. We've got to do a half. Now we've got to think about where theta's going from. So this point here, that's when theta is 0. And if you remember, you got one full lap of the circle just from theta going from 0 to pi. And then the function is cos theta. So we need cos squared theta d theta. That's what we've got to integrate. And to do that, you need the usual double angle formula for cosine that comes up so often. Cos 2 theta is 2 cos squared theta minus 1 over 2. And you are familiar with rearranging that, and you get that cos squared theta is equal to cos 2 theta plus 1 over 2. And now it's in a form where you can just write down an antiderivative to calculate that integral. So what have I got? I've got a half, and there's another half inside, so that gives me a quarter. Then I need an antiderivative of cos 2 theta, which would be a half sine 2 theta. And an antiderivative of 1 with respect to theta, that would be theta. And we've got to evaluate from 0 to pi. Now, when you plug in 0 or pi into the sine, you just get 0. So we're really just evaluating the theta between 0 and pi, and so we get pi, and the quarter gives us pi by 4. And that is indeed the answer that we were expecting. So it appears the method works. Good. So let me see. The last thing I want to do with polar graphs right now is I want to give you one more interesting example. This is known as the cardioid. So this is a kind of famous and fun example of a polar graph. So this is rather like the cycloid, which we saw last time. You remember for the cycloid, we were rolling a circle along the x-axis. Well, for the cardioid, we're doing something a little bit different. We're taking a circle and we're rolling a circle around another circle. So let's draw a circle, the grey circle here. That's going to be the fixed circle. And then I'm going to take a moving circle. I'm going to put side by side to that one, just touching it there. Let's make the moving circle for now. Let's make that change color. So that's going to be red. Okay, so it's the usual business. I'm going to take a circle of radius A, and what I'm going to do is I'm going to roll the red circle counterclockwise around the fixed grey circle. Okay, so instead of rolling along a straight line, I'm rolling around a circle. And then the cardioid is going to be the curve that's traced out by some special point on the circumference of that rolling circle. Okay, so this red circle is rolling around the grey one. There's no slipping going on at the interface. They're kind of meshed together. So let's see. Let's say that special point is at the origin initially, that x. And let's just picture a couple more places that could be. So a little later on, it'll have rolled around a little bit. Let's make that blue circle a little bit later on. And how about we do maybe when it's got halfway round, let's make that green circle there. Look, there we are. That's when it's gone halfway round. So you can kind of see what's going on. So in the blue circle, that mark point is going to be there, that special point on the circumference. It will have rolled around a little bit. And what about in the green circle? So when it's got halfway around, that special point is going to be exactly on the opposite side there. And then maybe I've plotted enough points for you to sort of picture what's going on. Maybe I should plot one more a little bit. Let me do a slightly better picture. So let's plot one maybe up here in the middle somewhere. How about that? And we'll make that a purple circle. There we go. So in the purple circle, where's our marked point? It's going to be so that that distance around the grey is going to be equal to that distance around the purple. So I reckon it's going to be about there. And then I'm going to sort of plot these mark points together, it's going to look a bit like that. And then it's symmetric down below, so it's going to look a bit like that. So that curve that I've tried to draw there, that heart-shaped curve, that's the cardioid. Okay, so let's see if we can calculate the equation in polar coordinates. So what I'm going to do is I'm going to treat this blue circle as being kind of general position. So we're going to assume that, so what I'm trying to do is I'm trying to find the polar coordinate equation for that special marked point on that blue circle. I think I need to zoom in because this is a little bit confusing without a good picture. So let's try and draw a good picture. So I'm just doing my best effort at drawing a picture. There we go. Actually, I want that to be a little bit, it's not quite straight down, it's at a little angle. How about that? That's not too bad. Okay, so let's fill in a few points. So this right here, this is the origin. And then right here, this is the special point we're after. So we're trying to find the polar coordinates of the special point on that circumference of that blue circle, which is kind of my general position. And let me see, this is the center of the gray circle. This is the center of the blue circle. This point here, that's that point exactly where the blue and the gray circle touch. So that's a radius, that's a radius, that's a radius, and that's a radius. And let me see, because the blue circle and the grey circle, there's no slippage, that arc length there along the grey circle and that arc length there along the blue circle, they're exactly the same. So that arc length, that tells you that that angle and that arc length is that, it tells you that that angle and that angle are both equal. So that's that angle and that angle in my picture. And since that's A, that's A, that's a straight line, that's A and that's A, and those angles are equal, I think you see right away from that that this side and this side, they are parallel lines. And so since they're parallel lines, that angle there and that angle there are actually the same angle as well. And that's the angle theta of this special point, this blue marked point that we're trying to calculate. And you see what we're trying to do then? We're trying to find what r is as a function of that theta. So as theta varies, we want to know how the radius varies. That will give us this function, giving us this polar equation. Okay, so that's pretty good. What else can I fill in here? Let me see. This triangle right here, this is an isosceles triangle, side A, side A. Let's call that side there B. If I were to drop that perpendicular, so that would be half theta in there. That angle there, that would be pi by 2 minus a half theta, because the angles inside this add up to pi, and one of them is pi by 2. So that angle there, let's name that angle there. That angle there is going to be pi over 2 minus theta over 2. And if I were to do SOHCAHTOA in that right angle triangle, the opposite side is b over 2, the hypotenuse is a, and there's the angle theta over 2. So we would get that sine is opposite over hypotenuse. I get that equation out. Okay? But let me see, this triangle and this triangle, they're just identical. So in exactly the same way, this is going to be b here, and that is also going to be pi over 2 minus theta over 2. So then we can think, what's this angle right here? You see, this is a straight line, so that's pi. But from that and that, I've already got pi minus theta. So that means that that remaining angle there, that must be just another theta. And here, I've got another isosceles triangle, two sides B and B. So again, I'm going to drop the perpendicular there. This side length here is r. That's what I'm after, right? The distance from our special blue point to the origin. So I'm trying to calculate r, and I can do it by doing SOHCAHTOA in that right angle triangle. The angle is theta over 2. That opposite side is r over 2, and the hypotenuse is b. So my sine theta over 2 is also equal to opposite over hypotenuse. And from that, if I cross multiply that second equality, I get that b squared equals ar. So we've nearly done all the difficult stuff. The one last clever thing to do is to think about cos theta. We know sine theta over 2, but I can write cos theta in terms of sine theta over 2 using the double angle formula for cosine. It's the same as 1 minus 2 sine squared theta over 2. Okay, so I'm not using theta and 2 theta, I'm using theta over 2 and theta. But that's just our usual double angle formula for cosine. So what have I got? I've got 1 minus twice. Now sine theta over 2 is b over 2a. So that gives me that cos theta is, okay, so if I square all this, what have I got? I've got 2b squared over 4a squared, which is the same as b squared over 2a squared. But b squared is ar. We found that earlier. And then one over the a's cancels, and I'm left with 1 minus r over 2a. And then if I just rearrange a little bit, I get r over 2a is 1 minus cos theta. And so r is 2a, 1 minus cos theta. So there it is. There's the nice polar equation for the cardioid derived for you. I'm not actually going to do anything with that right now. I wanted to derive it because I'm going to get you to do something with this on the homework. I'm going to get you to calculate the area of cardioid. And so to do that, you'll need to know the equation, and then you're just going to use the formula for area of a sector of a polar graph. So putting those two things together is quite a fun exercise to find the area of that cardioid. Okay, I think that's a good moment to move on from polar coordinates, but we'll be back. Remember, what I want to do next is go back to conic sections, and we're trying to eventually transform the equations for the conic sections, the ellipse, the parabola, the hyperbola. We want to write those equations in polar form, because that's really the most natural way to write those equations. That's what we'll need when we're doing planetary motion. So we're going to go back to conic sections. Now we know a little bit more. So I didn't do that much with conic sections yet. I explained the definition, and I think I mainly focused on the ellipse when I was working through that before. So let's just review what we know about the ellipse. That's the one we're best at. So let me see. So here's an ellipse. Here we go. And so for the ellipse, you want to have a greater than or equal to b, and then that's the coordinate x equals a, and that's the coordinate y equals b. So that's minus a, that's minus b. And so you remember that this ellipse, this was its standard rectangular form, x squared over a squared plus y squared over b squared equals 1. Good. And then we did talk a little bit about so that's the Cartesian equation for the ellipse. We talked about the good old Euclidean geometry formulation, which was this equation. So here you needed two foci. So there was focus F1 and focus F2, and then the ellipse was all these points P equals XY. such that the distance from P to F1 plus the distance from P to F2 was a constant. And I think we just did talk about how to find that constant. If you think about that particular point on the x-axis on the ellipse, that was that distance from F1, that distance from F2, and it was the same as that. Oh yes, that was 2a. So the constant is 2a when you're using these a's and b's the way I am. Okay, so remember this was the major axis and this was the minor axis of the ellipse. So when I did this, I started with genuine conic sections, and I derived this equation from the general conic section description, and I derived that equation by a different method. And I think I left it for the homework for you to go directly from the Cartesian to the Euclidean equation for the ellipse. So let's see. I think I should do one more thing. I should wonder about where are the foci in the ellipse. So let's label F1, let's say that's at x equals c, and then F2 is going to be at x is minus c. How do you find c in terms of a and b? So this is kind of nice to do, actually. So what you do is you think about this moving point, you put it instead of the other really distinguished point, which is where this ellipse crosses the y-axis. And for that point, that length to F2 and that length to F1 are just equal. And since those two lengths sum to 2a, that means that that length must just be a. And then you can just use this right-angled triangle. That's width c and height b. And so you deduce quite quickly that if I just do Pythagoras, the hypotenuse squared is the height squared plus the width squared of this right-angled triangle. So thinking about that special point gives you the relationship between c and a and b. In fact, c is going to be, c squared is a squared minus b squared, so c is the square root of a squared minus b squared, which is, I like to pull out the a, it's a root 1 minus b squared over a squared. So this quantity here has a special name. It's called E. It's the eccentricity. And so what we've just shown is that the C, the coordinate of the focus, is AE, where E is square root 1 minus b squared over a squared. Let's put a little box around that because those are quite useful formulas to remember. And we've just derived those from our geometric description and the Cartesian equation. So let me see, it's important for the ellipse that a is greater than or equal to b, then this quantity is between 0 and 1, and so when I do one take away that number, it's a positive number, and that square root makes sense. Why is it called eccentricity? Well, a special case of the ellipse is when a equals b. When a equals b, that's just 1 minus, that's just 0. So the circle, when a equals b, the circle is the ellipse of eccentricity 0. And then in general for the ellipse, the eccentricity is between 0 and 1. So E equals 0, that's when the ellipse is actually a circle. Okay, that's all good. So let's see. Let's maybe talk about the hyperbola briefly. I must say I usually spend the least amount of time on the hyperbola. I'm going to spend a long time talking about parabolas next time because the parabolas I rather enjoy. But let's say a little bit about hyperbola. That's sort of the ugly cousin in the three. So here we go, hyperbola. So let's sketch hyperbola. So you remember hyperbola, you have these diagonal asymptotes. So there's one asymptote, there's the other. And then the hyperbola goes through x equals a, and it approaches that asymptote, and then by symmetry it's minus a, it approaches that asymptote, Okay, so that's my attempt at sketching the hyperbola. So its standard rectangular equation is x squared over a squared minus y squared over b squared equals 1. So you see where a is, right? A is the axis, the x-axis intercepts, but it's not so easy to see b from this picture because it doesn't cross the y-axis anywhere. There's no other special points to think about. So what you have to do is you have to actually think about the asymptotes. So those dashed lines, those diagonal lines, what are they? And so you have to think what happens when x and y are both very, very big. When x and y are both very, very big, you may as well forget about that 1 and replace it by a 0 because it's kind of negligible in comparison to x and y. And so to get the asymptotes, actually, that's what you do. You just change the 1 to a 0, and that's the equation that tells you what those asymptotes are. If I make y the subject, what y squared is b squared x squared over a squared, so when I square root, y is plus or minus b over a x. And that tells you that the slope of that line, of that diagonal asymptote, is b over a, and I guess that one is of slope minus b over a. So the upshot of this little calculation is that, I mean that's a, right? So that height of that right angle triangle going up to the asymptote, that must be b. So that the slope of that line, rise over run, is b over a. So that's how you can see b in the graph of the hyperbola. It's the slope of that it tells you the slope of that diagonal asymptote. Okay, good. So let me see one more thing about hyperbola. I've given you the Cartesian equation, but it also has a nice Euclidean equation. So for this, there are again two focuses, f1 and f2. And you can describe the hyperbola nicely as at the points so that the distance to f1 and the distance to f2, it's not that the distance is sum to 2a. Now you have to look at the difference in those distances. So the distance from p to f1 minus the distance from p to f2. That difference, let's put absolute values around, that difference is a constant. And just like for the ellipse, to work out what the constant is, you look at this special point here. And so the difference, that distance minus that distance, which is that distance minus that, it's just that distance there, which is 2a. That's your constant. Okay, so the constant's just 2a, just like it was in the Euclidean equation for the ellipse. Great. So that's the equation, and I'm not proving that these two equations are equivalent. It's very similar to the proof in the case of the ellipse, which you did on a homework. So I think you should be able to work that out for yourself. It's true. But let's again answer this question: where are the foci? So I'm going to put the foci at C and minus C again. How do you calculate C in terms of A and B? So this is not quite so obvious as when we had the ellipse. The way we worked that out was I looked at that other distinguished point on the ellipse where it crosses the y-axis. But there doesn't seem to be any other obvious point to consider in the hyperbola. Well, what you have to do is you have to sort of consider a point sort of very far away. You sort of have to look at this point at infinity. You take some point way, way up there. So let me just try and explain that. I think you just need one good picture, and then this is quite easy to understand. So let's draw a great big hyperbola. And I want some diagonal asymptotes. So here we go, some diagonal asymptotes. Let's make it go through the origin at least. There we go. And another diagonal asymptote that's sort of up here. Oh, I want it to be a straight line. There we go. And That nearly hit the origin. Look, I nearly got lucky. Let's move it a little bit. So those are my diagonal asymptotes. And then I'm going to just draw in the hyperbola. So I'm going to go kind of at A here and at negative A. And so here's the hyperbola approaching that asymptote, approaching that asymptote, approaching that one. That was a little too close for comfort, really, and coming down there. Okay, good enough. Not perfect, but you see the idea. And what we're trying to do is we're trying to work out C, where the foci are, minus C. And I've already noted one piece of information which is useful, is if I draw that right angle triangle in there. There we go. So that's that right angle triangle. I've already noted that that's length A and that's length B. So this length right here, that's going to be by Pythagoras square root A squared plus B squared. Okay, so now what's the trick then? So we're going to look at a point that's sort of up here, way, way away. I can't quite draw far enough away. So let's just sort of go, well, maybe I'll just go a little bit further and I'll draw some point here. So you've got to imagine this point P being a long way away from the origin. And here were the foci. So then what we've got to do is we've got to look at the distance from P to F2 minus the distance from P to F1. And the point is that because P is very far away, I can get away with just dropping this perpendicular from C to the diagonal asymptote. So that's another right angle. And because P is very, very far away, that angle there is going to be very, very close to 90 degrees. And so this, and I mean, I may as well basically treat P as being on that diagonal asymptote. And that's going to be pretty much an isosceles triangle. This length is going to be absolutely negligible compared to how far away P is. So the distance from P to F1 is pretty much the same as the distance from P to that orthogonal projection. Similarly with F2, if I project my second focus on to that asymptote, the distance from P to F2 is going to be pretty much the same as the distance from P to that point. Okay, and then we want the distance from P to F2 take away the distance from P to F1 to be 2a. So we want that length take away that length, which is just that length, to be 2a. Well, this is the middle, so from that thinking, you deduce that this length right here is simply a. Okay, now we're nearly done. It's kind of a little bit of a long-winded argument, this. Now there's some similar triangles. I've got this triangle here, which is right-angled with this angle in it. And I've got this triangle here, which is also right-angled with the same angle. And so in similar triangles, ratios of corresponding pairs of sides are the same. So if I just use similar triangles, so let's see, let's look at the hypotenuse over the adjacent side in that triangle. So that's root a squared plus b squared over a. And similarly in the other triangle, hypotenuse, which is c, over the adjacent side, which is a. We get that that's c over a. Therefore, a squared plus b squared square root equals c, or the way I prefer to write it, c, I prefer to pull out the a. C is a times the square root of 1 plus b squared over a squared. And this number here is again called e, the eccentricity of the hyperbola. Okay, so that's that little analysis. So the upshot is that again, c is a e, where e by definition, is the square root of 1 plus b squared over a squared. That's the eccentricity in the case of the hyperbola. So it's very similar. The only difference is that in the formula for eccentricity for ellipse, there was a minus there. For hyperbola, there's a plus there. And so if you think about that, that means that for the hyperbola, this thing called the eccentricity is bigger than 1. Okay, so eccentricity 0 is a circle, between 0 and 1 is the ellipse, bigger than 1 is the hyperbola. Well, we're just left with the parabola. So the parabola is the conic section of eccentricity 1. That's that last case for E. So let's quickly just say a tiny bit about parabola. So that's E equals 1. So I think I like the equation 4ay equals x squared. There isn't really a standard here. So let's take that equation for a parabola. Maybe you're just used to y equals x squared, but it's been scaled as this extra parameter a in there. So that's roughly the parabola. So that's the Cartesian equation for the parabola. But let's see if we can get to the Euclidean equation. So there is actually a focus in here, f1, which is up at on the y-axis distance a from the origin. And let's think about some general point P on the parabola. So P is xy. And what I'm going to do is I'm going to try and calculate the length PF1. So I can do that just by drawing a little right angle triangle. I always manage to get a very skinny triangle when I do parabolas. So what have we got here? So PF1, so that's the hypotenuse of that triangle. So we need to know this, well, that's just x, right? So the hypotenuse's length by Pythagoras is the square root of x squared, and then I need this height, so that's not y because that's a, so that's actually a minus y. Okay, so let's calculate that. So it's where x squared is the same as 4ay because that's the point on the parabola. And if I FOIL out the other guy, I get a squared minus 2ay plus y squared. And that's quite nice because I've got the y squared, I've got 4ay, take away 2ay, so that leaves 2ay plus a squared. That's that length. And hopefully you recognize that that's y plus a all squared in there. So I can square root it and I get y plus a. So the conclusion of this little calculation is that if I draw another line down here at minus a, so let maybe draw a little dashed line here. So that's the line y equals minus a. So this has a name. This is called the directrix. The directrix of that parabola. And okay, my picture's never very good because I want to draw that length there. So that's the orthogonal projection of the point P onto the directrix. So that gives us another point which, so let's maybe go into blue because that was my usual convention. So that point there I'm going to call F2. And then what we see is that this y plus a distance, well, that was y, and that's a. So y plus a is actually the distance from P to F2. So this shows that at least for that parabola, the distance from P to F1 is equal to the distance from P to F2, where F1 is the focus and F2 is the projection of P onto the directrix, y equals minus a. So this is the Euclidean definition of the parabola. You have a focus and a directrix, and the parabola is all points whose distance to the focus is equal to the distance to the directrix. Okay, that's enough about parabola. Right now I'm going to stop, but I'm going to say a lot more about parabolas in the next lecture.